Hello everyone, my name is Angelia and I'm here to discuss our second project for our hardware architecture for deep learning course, anomaly detection using unsupervised learning. What is anomaly detection? Anomaly detection or outlier detection is the process of identifying data points, events, or observations that deviate significantly from the dataset's majority. Why do we need to do this? This helps us identify technical glitches, potential opportunities, and most importantly, malicious activities like fraud. So, we categorize this into two: supervised detection, where we have a fully labeled data set, normal versus anomalous. And second is unsupervised detection, where there are no labels provided and the system must infer everything from the dataset's intrinsic structure and density. So we are focusing mainly on the unsupervised part here. Giving some domain specific context, we are doing this in two different domains in our project. One is financial transaction systems and one is time series data. So for financial transaction systems, what we do is for big enterprise resource planning systems like SAP, they generate massive logs of financial journals, and fraudulent transactions make less than 0.01% of the data set, and it create the major problem here is identifying the extreme class imbalance, needle in haystack problem, and identifying the fraudulent transactions from the normal transactions. So we have to detect these local anomalies that, and these frauds actually mimic normal behavior, so identifying them is actually very difficult, and they occur in a rare combination of attributes. For time series data, what we do is this time series data has a temporal dimension. The anomalous value is not just an extreme number, but it's a deviation from our expected sequence. So the key challenge here is distinguishing between these anomalies and these benign changes, which are not actual anomalies. And for example, there is a high server load on a day, which is in during daytime, which is normal, but a spike at 3 a.m. is actually anomalous. So let's discuss the previous work that has happened in both these domains. For anomaly detection in finance, historically this was done using rule-based systems or expert systems. The mechanism is basically that there was hard-coded logic which used to flag transactions as red flags, and the problem is they used to give very high positive rates, because even an extreme number could trigger as an anomaly, which would lead to a lot of auditor time, wasting auditors time, which creates a lot of problems. Then we transition slowly into machine learning, where we use principal component analysis (PCA) and isolation forest. Isolation forest is where we randomly split data on basis of attributes. And how do we detect the anomalies? Anomalies are detected by identifying the fewer splits that happen in these isolation forests. Therefore, we can detect our anomalies. And slowly we shift towards deep learning, where we use auto-encoded neural networks, AENNs, which basically compress and reconstruct normal transactions, so that the model learns the complex manifold of these normal transactions. And what happens is when it comes across an abnormal transaction, what happens is the reconstruction error will be very high, and therefore we can isolate it. Then anomaly detection in time series usually uses statistical forecasting models like ARIMA, auto-regressive integrated moving average. This method, where we have a linear combination of past errors and past values. And the limitations are that these assume linear relationships between the data and require the data to be stationary, which the data is not actually stationary. It can't identify non-linear interactions and multivariate data. So this causes a big problem. And then we transition again to deep learning, where modern approaches like CNN and RCNN and LSTMs are used to predict data, not based on statistics, but based on these deep learning networks. And the difference between the deep learning forecast and the actual value is found out. And if the anomaly exceeds the dynamic threshold, the anomaly is flagged, and therefore we can isolate these events. Okay, so let's move on to the justification for our approach. The selection of deep autoencoders for financial data and CNN based model for time series data is based on specific theoretical and computational advantages over traditional methods. So, the financial model, why autoencoders outperform linear models. So, the first part is the nonlinearity and manifold learning. The limitation of PCA is a linear transformation. It assumes that data lies on a linear hyperplane. But when we come to the autoencoders, they have an advantage. By using nonlinear activation functions such as leaky ReLU and multiple hidden layers, autoencoders perform manifold learning. So the bottleneck effect is where the core strength of our architecture, which lies in the latent layer. So by forcing the network to compress the input into fewer dimensions, we create an information bottleneck. Now let's move to the time series domain. Why CNNs outperform RNNs and LSTMs. For sequence modeling, we usually use RNNs or LSTMs for anomaly detection, but we have chosen to use CNNs. The advantages are that the local feature extraction. We usually in time series data, we often rely on shape changes such as sudden spikes, dips, and jitter. The CNN advantage is excellent at detecting these morphological features. And the computational efficiency is that limitations of LSTMs is that we have a lot of steps involved in LSTM, which is sequential and step by step, which makes training super slow. But the CNN advantage is that the entire window of data is processed in parallel, which makes it completely efficient. And the unsupervised advantage that we are using in both our models is that the flaw of supervised learning is the lack of labeled fraud data. Our approach is that we train our model on strictly normal data, which is unsupervised, and the model understand what normal looks like, and then it can further understand when this data deviates from this normal, and then we can automatically flag these transactions, and this is future proof. Okay, we move on to the first part of the projects, which is the anomaly in financial transactions using autoencoder networks. So the first thing that we use here is it's centered on accounting information systems AIS and enterprise resource planning environments. And as illustrated, the data flows hierarchically. In the first we have business processes, which is the operational layer, the accounting information, which is the financial abstraction, and the journal entries, which has the technical database data. Okay, so let's get a data set overview of the financial transaction data. So the data set we used is used to simulate real world financial transactions within an accounting information systems AIS or an enterprise resource planning system. So we used SAP's FICO module, which comprises 5,33,000 rows and 10 columns of transactional data. The original features contained 7 categorical, 2 numerical columns, and a label column to indicate the transaction type. And then for the anomaly detection, the distribution of anomalies, the data set is highly imbalanced, containing only a small fraction of anomalous transactions. In total, there are 100 anomalous transactions, which makes up only a mere 0.018% of the entire data set. And for the pre-processing steps, we handle the categorical data. We identified the categorical attributes. There were 6 categorical attributes, and the method we used is one-hot encoding, and we use pd.get dummies to get the to convert the categorical values into binary data, thus increasing the dimensionality of the data set. And to handle the numerical values, we use log scaling and min-max normalization, where the numerical values were first log scaled. That means they were symmetrical. They were made more symmetrical using a small epsilon value, 10 raised to minus 7, and to avoid the issues with zero values. And then we scaled them using natural logarithm. And we also use min-max normalization, where the values were normalized to a range between 0 and 1. And finally, we merged all of them together using pd.concat, and we ended up with 618 columns in our dataset. Okay, so let us get to the architecture that we've used here. We have used an autoencoder neural network, AENN architecture, and the goal of an autoencoder is learn a representation or encoding of the set of data and then understand the features. First we have our input data, which had like 618 features, like we discussed before. So it is passed on to the encoder network. So the encoder network transforms the 618 input features to 10 output features, that is to a shrunken latent space. So the activation function that we use here is nn.leaky_relu with a negative slope of 0.4, and this is used after the linear transformation, and the weight initialization is done as nn.xavier_uniform to initialize our weights. And at the decoder network, after the encoding is done, we have 10 neurons to match the latent space size, that is the 10 output features that we had, and this is transformed back into 618 output neurons. And our activation function that we've used is similar. It's the nn.leaky_relu that we used in the encoder part, just to keep it symmetrical, and the weight initialization is again nn.xavier_uniform. And our training objective is to optimize our loss function. Our loss function is nn.bce with Logit's loss, and this is a binary cross entropy loss function and is well suited for our data. And we also have to have an optimizer. Our optimizer that we are using is Adam optimizer with a learning rate of 10 raised to minus 3, and this architecture is highly suitable for a compressed representation of the 618 dimensional financial transaction. And let's move on to how we train the model. So to train the model, we do a forward pass of the encoder decoder part, compute our binary cross entropy loss reconstruction loss, and then we do a backward pass of the encoder decoder part and update the parameters encoder f theta and decoder g theta networks. Our total epochs were 50. And the learning rate was, as told before, 10 raised to minus 3, and the total time taken was 23 minutes. Okay, so let's move on to the results portion of our first part. We have our graph that illustrates the reconstruction error for over the 50 epochs. So for the first 0 to 10 epochs, we have rapid initial convergence, and then from the 10 to 20 epochs, we have diminishing returns and fine tuning, and we have a stable plateau after 20 epochs. So that can be seen from the graph. And next we have our scatter plot for our anomaly detection, where we have regular transactions shown by the blue circles, and we can see the reconstruction errors are constantly below 0.015. And let's look at the global anomalies. The global anomalies are the orange triangles or the red flags, and we can also see that clustering primarily occurs between 0.06 and 0.08. Local anomalies are the green triangles or the hidden thread. They happen in the 0.02 to 0.06 range. And overall, all of this visualizes the needle in the haystack problem that we described earlier. Our model has total detected over 91 anomalies out of the 100 anomalies based off of the 0.2 threshold that we found from the scatter plot. And we detected all of the 70 of the global anomalies, and it also detected 21 out of the 30 local anomalies perfectly. The threshold value optimization techniques can further improve this. So then we also have our precision and recall against the threshold graph, where the green line shows the of the total actual fraud cases, what percentage we found, and the blue dashed line, which is the precision graph, shows the transaction that we flagged as fraud and the percentage of that which was actually fraud. The narrative of the graph is that the blue line precision shoots up vertically around the threshold 0.01, and this is where the model stops confusing the normal transactions for fraud. And we also have these missed opportunities where the recall drops sharply around 0.07 threshold, and the final conclusion for our report is that the precision is very near to 1, which is what we need, and the recall is greater than 0.9. Okay, now we move on to the second part of our project, which is time series data anomaly detection using CNNs. So static detection normally focuses on the point anomalies, which are individual values that are extreme, but time series detection requires understanding temporal context. Traditionally, this was done using dominated by statistical forecasting models and manual rule-based systems, but these traditional models fail to capture complex nonlinear dependencies. So our project explores the deep learning part which can further improve this. So our project mainly focused on the computational efficiency and parallelism and local feature extraction using CNNs, and it also improves the robustness via unsupervised forecasting. Okay, let us move on to the dataset description for our time series analysis. We utilize the air quality dataset obtained from the UCI machine learning repository. This dataset contains the responses of a gas multisensory device deployed in a field in an Italian city. The primary goal of using this dataset is to check the model's ability to detect environmental anomalies. The data structure and characteristics involve missing values tagged with -200, and attribute information involves 15 attributes mixing ground truth with reference measurements derived from certified analyzers and raw sensor responses. Now we do a few pre-processing steps for deep learning where we do parsing, that means merging the date and time into a single timestamp index, cleaning, replacing the -200 values as said earlier with linear interpolation, and decimal conversion, changing the comma format to an actual decimal floating point format, and normalization involves taking all the data values and fitting them into a 0 to 1 range. And we also do sequence generation where we focus on the window size W, input X, and target Y. And we also do train, val, and test split where we do the training. We have the training set, the validation set, constitutes 10% of the total, and test set, which also constitutes 10%. Okay, now let us look at the model architecture for this. We are using a convolutional neural network designed specifically for time series forecasting. Unlike recurrent neural networks, it is not sequential. It treats a window of time series as a fixed 1D image. We use the convolutional module for feature extraction and a fully connected module for regression and prediction. Our input representation consists of N, the batch size, C, the number of channels, and L, the length. It's a 3D input tensor. And when we move on to the convolutional module for feature extraction, we have the block 1, which is for short-term pattern recognition, which has 64 learnable filter slides, and the function is that it detects intermediate short-term temporal dependencies. We use ReLU activation function and max pooling. For block 2, we have high-level feature abstraction, where we do a point-wise convolution of kernel size 1, which increases the depth of the feature map from 64 to 128. Since the kernel size is 1, we do not look at temporal neighbors. Instead, this acts as a channel projection layer. We also use max pooling here. The fully connected module, which is the second module that we use for forecasting, does flattening. It also has a hidden layer which maps the flattened features to a hidden dimension of 256 units. It also does regularization and also has an output layer which maps the hidden state to the output dimension C. Finally, to accurately train the forecast time series trends, we treat the problem as a regression task, and the primary objective is to minimize the discrepancy between the model's predicted output and the actual ground truth. So as I said earlier, we treat the problem as a regression task. We employ mean absolute error as our loss function, and it's chosen for its robustness. For our anomaly detection mechanism, once the time series predictor is trained, the anomaly detector module operates by comparing the forecast against the real-time sensor data. We quantify this deviation by calculating the Euclidean distance, which serves as the anomaly score. A low score indicates that the system is behaving as its normal expected behavior, and a high score indicates a significant deviation from the learned pattern. In the final stage, we change this continuous anomaly score into a binary decision, and this is done by dynamic thresholding. The mathematical formulation for this dynamic thresholding is done by assuming that the data forms a normal distribution, and theta is equal to mu plus alpha sigma, where alpha is the sensitivity factor and sigma is the standard deviation, where mu is the mean. And our decision logic involves any error falling in between the range mu minus 2 sigma to mu plus 2 sigma. We categorize it as statistical noise, and any error exceeding that will be treated as an anomaly, and all these events are thus flagged. Okay, now we move on to the results portion for the second part, where the calculated thresholds and the indices where the anomaly was detected is shown. And The visualization for each feature is split into a forecasting task and a detection task. The forecasting performance is the target versus prediction. The blue line or the validation sequence represents historical data where it fed into the model during the validation phase, and the green dashed line represents the ground truth for the test set, and the orange dotted line is the predicted sequence. This is the model's output. It shows a good fit when the orange line sits on top of the green line and the model is accurate, and it also shows a gap where the orange line is lower than the green line, and this gap is the reconstruction error. The right panel shows the anomaly detection or the flags. The solid blue line, the data sequence, gives the continuous timeline of the actual sensor data, and the red dashed line or the vertical line is the temporal boundary, and it is around time index 950. The red dots are the anomaly points at the specific timestamps where we have flagged an anomaly. We see a cluster of red dots around time 1000 and time 1400, and looking back, these correspond to the moments where the green line spiked upwards but the orange line failed to keep up. This suggests that an anomaly is a sudden intensity spike or a sudden cloud of exhaust gas deviated from the expected trend. So, our project successfully demonstrated the efficacy of deep learning techniques in overcoming the limitations of traditional rule based anomaly detection systems. We used two different types of architectures: one autoencoders for high dimensional tabular financial data, and 1D convolutional networks for sequential time series data. We established a robust framework to detect local anomalies and 0-day irregularities without the need of labeled fraud datasets. Thank you.